Welcome to the L2 conservation of energy in our energy unit. Make sure that you have your note sheet out and ready to go, and you're listening for those hidden talking points. There will be 2 or 3 throughout this video. Letter I is about changing forms of energy. So when we talk about conservation of energy, we're talking about how energy is never lost, it's never created, and it's never destroyed. It's always just changing from one form into another. Letter A says energy is most noticeable as it changes forms, such as hearing music through your phone, a book falling from a shelf, or a car speeding by. In all these cases, energy is just being transformed from one form to another. In the car, the chemical potential energy that is in the fuel is being transferred into the motion of the car, the sound that you hear when the car goes by, friction and heat going into the road. Same thing with the books. The books have stored gravitational potential energy when they're on a shelf. Now, if the shelf breaks or if somebody knocks the shelf, the book's energy goes from gravitational potential energy and it goes into kinetic energy until it hits the ground. When it hits the ground, it's transferred into sound energy. It can be transferred into heat, sometimes in friction, all types of other things. Letter B is about the transfer of electrical energy. Basically, what's happening here is electrical energy is changed to light in a light bulb. If you put your hand close, you feel heat. This shows that electrical energy is also changed into heat. So, this is just one example of how you see different forms of energy. So, in the light bulb example here, if you look, you turn the light switch on. Now electrical energy is coming through from a power plant or somewhere, and what a light bulb does is it just converts that energy into light and some heat. Next we're going to talk about transforming chemical energy. Fuel is stored in the form of chemical potential energy. When you eat food and then go for a run, food is changed from chemical potential energy to kinetic energy that lets you move. So this guy on the left over here, he probably had a nice breakfast or something before he went for his run, and all that stored energy that comes from his food is going into the energy that actually allows him to be able to run. Another type of chemical energy is seen in photosynthesis. And in photosynthesis, what happens is plants are actually creating chemical energy. And what plants do is they actually convert light energy. So your first blank down there on the letter, your II is light, and they convert light energy from the sun into chemical potential energy that makes up the plant. So plant material itself is chemical potential energy because we can eat the plant and we get some energy from that. Now we're going to talk a little bit about conversions between kinetic and potential energy. Kinetic and potential energy are very, very tied in together. And most events that we experience use kinetic, that's an N, and potential energy. And this is such as riding a bike or shooting the bow and arrow. To identify the changes in energy, we use something called mechanical energy. So in the example on or above here, in the bow and arrow, what's happened is that we're assuming that he's pulled the bow and arrow back, which is kinetic energy, changing to potential, and then when he releases the bowstring, all the potential energy he stored up is going to transfer back into the kinetic energy of the arrow. Letter B here is talking about mechanical energy. So the very first thing you need to write here is mechanical energy. And what mechanical energy is, it's the total potential and kinetic energy of a system, which means mechanical energy is due to kinetic and potential energy that an object has. So if we want to measure how much mechanical energy, let's say, the arrow has above, we would measure its kinetic energy and its potential energy, because once it's shot, it has some of both. Alright, now we're going to make little bar graphs comparing the amount of potential energy and the amount of kinetic energy in the pictures. In this very first picture here, you can see that the apple is still sitting at the very top of the tree. So if the apple's hanging from the tree, that all of its energy is going to be potential energy. So we're just making a bar graph here. And remember, the numbers don't matter. We're just comparing kinetic to potential energy. Now there's no kinetic energy because the apple's not moving. Now in the second picture, if you look, the apple has fallen about halfway. So if it's fallen halfway, well, that means that now this big bar of potential energy, some of it's now been converted into kinetic energy. So we should have about half kinetic and about the same amount of potential energy here. So they should be about the same size because it's moving, but it still has the potential to fall further. It hasn't hit the ground yet. In this last picture, we're assuming the apple's just about to hit the ground. So all of its potential energy has been converted into kinetic energy. Alright, now we're going to look at the swingers on the bottom. So let's look at the picture on the right over here first. In this picture, the two people on the swing we're going to assume they're at the top of their swing. So they're at the highest point they could be. Now if they're at the highest, you know what's going to happen. We've all went on swings before. They're going to be falling back down to the ground at some point. So that means that they should have full potential energy because they're at the very highest, they're going to swing back through the other way. Now, if we look at the other side here, we're assuming these two people are still in the middle of a swing. So they just happen to be at the bottom of their swing. If you think about it, when you're going the fastest on a swing is actually when you're at the bottom. That's because all of that potential energy from when you're at the top has been converted into kinetic energy. Now we're going to talk about the law of the conservation of energy. And this law says that energy is always changing from kinetic to potential and back. But the total amount of energy is always the same. Letter B says the law of conservation of energy states that energy cannot be created or destroyed, which means the total energy in the universe is always constant. So that literally means from the minute of the Big Bang, everybody, that all the energy that the universe had when the Big Bang happened, it still has that same amount of energy right now. Letter C talks about energy conservation. You might have heard of this before, and what energy conservation or efficiency is it means how well your car or an appliance changes potential energy. So there you're going to write potential energy into kinetic energy. And that means without losing energy to heat or friction. So it means all the energy that it's converting is going into energy that we can use, not lost energy. Finally here, we're going to finish up by talking about letter D. And what letter D says, it says you might think that energy is not conserved because when you stop pedaling a bike, you will eventually stop. This is due to friction and air resistance. Some of the energy is even converted into heat and sound. When you brake on your bike tire, I think some of you know, like if you feel the tire after you brake, it's very hot. It's because some of the energy from your bike is being converted into heat, and you know that it makes a sound even sometimes when you stop. So some of it's being converted into a sound as well. Okay, we're going to talk briefly about nuclear fusion and nuclear fission. And now, these happen at nuclear power plants and on the sun as a couple examples. Nuclear fusion, inside the sun fuses the nuclei of hydrogen atoms together to make helium and gives off a large quantity of energy that warms us on the Earth. This is a special type of energy conversion. And so, for your first talking point, I'd like you to write that this only happens on the sun. Okay, the second type here is nuclear fission. This is when atoms are split apart in a nuclear power plant and give off heat, which is used to create steam and spin a generator. So the last word on there is generator. And if you didn't catch it, the first word should be split. Because in fission, what's happening is we have one atom that's splitting apart into two different atoms, and all this here is all the energy that it's giving off. So it's giving off a large quantity of energy. The very last thing is energy conversions in your own body. And letter A says, food is stored in your body as potential energy. So just like the apple has potential energy when it's hanging, food is potential energy in your body because you can use it later to move. It's stored in fat or other compounds, and it's used for a few things. It's used for moving your body, digesting your food, so that one's not on there, so you need to write digesting your food, and pumping your heart. And now, for your second talking point, I'd like you to write 2 other ways that your body can use energy. The very last thing, letter B, says that calories tell you how much energy you will get from food. When you eat breakfast, your body burns these for energy. So it uses those calories for the energy that you use. If you don't eat, it burns fat instead. And that is the end of lesson 2 on the conservation of energy.